A unitank is a vessel in which the processes of beer fermentation and conditioning can take place. Our advanced design centres around the creation of a batch beer fermentation flavour model with kinetics from the model by Guy and Ramirez. The fermentation reaction models the conversion of sugars and nutrients to ethanol and flavourings when yeast is added to the reaction mixture. The unitank model also considers a temperature regime which enables the reaction to progress through from primary fermentation to secondary fermentation to conditioning and finally cold conditioning. Moving on to the mass balances. Beer is typically 90% water by volume, therefore water is used in the reaction, however it does not take part in the kinetics. Equations 2 to 4 represent the growth equations for the three sugar components, glucose, maltose and maltotriose. The biomass production rate is given by equation 5. Yeast growth is limited by the availability of unsaturated fatty acids, so its specific growth rate term, μx, contains an inhibition term. Amino acids in the wort in equations 6 to 8 are consumed to form flavour compounds in the beer. Also included is the lag phase term D, which describes the amino acids lag phase that happens at the beginning of fermentation. Moving on to the products of the reaction. The fusel alcohols in equations 10 to 13 are produced from the fermentation of amino acids. They are considered undesirable in a beer and should be minimised. 14 to 16 are the esters created in the beer product. High concentrations of esters are desired as they contribute most to the beer flavour. 17 and 18 represent vicinal diketones and acetaldehyde flavours, whose final levels must be controlled so they do not dominate the beer. The final and most important product is at the top of the slide, ethanol, in equation 9. This equation assumes ethanol to be proportional to the amount of sugar consumed. Also on this slide are the specific growth rates of the sugars, which show how the sugars inhabit each other. With the fusel alcohols dependent on the amino acids, their mass balances were derived using amino acids reduction rates. And finally, the temperature dependency of the sugar's specific growth rates is given in the following form. The energy balance used for the batch reactor is given as follows. Fermentation is an exothermic reaction, so to implement temperature control, the reactor is jacketed. The cooling jacket is also used to implement the temperature drops needed to move through the different fermentation and conditioning steps.
All four main stages are completed within a unitank, dropping the temperature to transition through the stages. All stages have been modelled within the MATLAB code. The first step, which runs for 5 days, is fermentation at a temperature of 20 degrees. Then secondary fermentation is completed over the course of 2 days, dropping the temperature linearly from 20 to 12 degrees. After this step, 95% of the yeast is manually removed. This can then be transitioned to the conditioning step, where the temperature is linearly dropped over 2 hours from 12 to 5 degrees. Then for 7 days, the temperature is held at 5 degrees in the cold conditioning step. The key assumptions for the model are as follows. Water is not a reactant and stays throughout the regime. CO2 production is not modelled. We have constant volume, and yeast is instantaneously removed after the secondary fermentation step, which is at 169 hours. The model is based upon a batch reactor design. The main script is given here. The first step of this code is setting the simulation options for each of the 4 stages. Then functions are called into the main script. The first function is chemical species, which gives a structured array of all 18 chemical species within the unitank and gives parameters of molecular weight and density. The second function, called unitank, this gives the initial masses of all species and total initial mass in the reactor. The initial volume is calculated using a for loop to work out the total initial volume in the reactor. The initial concentration is calculated at an initial temperature set at 20 degrees. The next function is the reaction, which sets the parameters for the 3 main reactions in the reactor.
The next function is getConfig_monod, and this sets the parameters of the monod rate expressions that are used in the reaction kinetics. We also have getConfig_jacket, which specifies all of the jacket parameters. We use the aspect ratio to calculate the diameter and therefore the area. Down here we convert the jacket UA term into units of per hour rather than per second. getConfig_control specifies our controller parameters such as the gain, integral time, its limits and the initial value. We also have getConfig_setPoint, and this basically creates a vector of time and a vector of setPoint values, so each corresponding integration time point has its own controller setPoint.
Within the ODE solver are equations to calculate the conversions, volumes, selectivities, and the integral, which is the error between the set point and the output temperature, with respect to time. For these to work, initial values or guesses need to be specified. The yeast removal time has been soft-coded, so will always occur at the correct integration time step, allowing for changes in the fermentation time and the secondary fermentation time. Here, the integration time spans are set for each of the 4 steps. The sort function sorts this array of integral time steps in hours and into ascending order, and then the unique function is used to remove repeat time points. The initial values to be inputted into the DAE solver need to be specified in Y0. Further down, as we're using ODE 15S as our DAE solver, we need to specify our mass matrix with a 1 or a 0 inputted, depending on whether we are trying to solve an algebraic or a differential equation.
Because we require multiple different controller set points within our code, along with a step to remove 95% of the yeast after secondary fermentation, piecewise integration must be used. The for loop splits the integration into 53 different sections from 1 to the length of the integration time span minus 1. The find function then evaluates if the controller set point time or the yeast removal time equals the current integration time. The index return tells the ODE solver what event you are in terms of what set point regime the controller is in, and also if you are to remove yeast. Any new calculated values of set point and concentration of yeast are then passed into the ODE solver, which operates with the inputs Y0, options, and all other called structures such as chemical species. However, rather than running for the whole length of the simulation, the ODE solver now runs from one event to the next event using the vector integration timespan j to integration timespan j plus 1. Once the ODE solver runs the ODE script, it then concatenates the outputs and the initial conditions Y0 for the next piecewise integration are set to the end values of the output Y from the previous piecewise integration. In terms of the ODE solver, initially the dependent variables are defined, along with the rate constants, temperature dependency constants, and the rate laws for the growth rates as discussed in the kinetics. Then, the reaction rates for each of the 18 different chemical species are defined, again according to the kinetics discussed in the presentation. Moving on to the energy balance, the heat transfer rate to the jacket is calculated, along with the heat generated from the reaction. These are then used to find the rate of change of temperature in the unitank. The controller set point is then set to the defined value that matches up with the integration time, as previously discussed in the main script, and then this is used to calculate the integral for the PI controller, which is then in turn used to calculate the manipulative variable, which is the jacket temperature, and this is used to control the unitank temperature. Finally, all of the algebraic equations are solved and the ODE outputs are returned. We are now going to run the code, and one thing to note is that all of the figures are plotted in a single window with multiple tabs.
So this graph shows the concentration of the main components in the unitank. The sugars, all 3 of the sugars, decrease with respect to time, particularly glucose, as the reaction has a higher affinity for glucose, and then the ethanol concentration increases. All consumptions and productions dramatically slow after 95% of the yeast has been removed. This graph, these 2 graphs, you can see the different temperature profiles for each of the 4 steps, with the jacket temperature being manipulated to control the temperature within the reactor.
This graph shows the concentration of the amino acids within the system, and these 4 graphs show the concentration of the ale flavours. So if you look at the concentration of phenyl diketones, that has a maximum limit, and if the concentration were to go above that limit, the flavour of the beer would be ruined. The next graph is for the ale ABV, so you can see that the final value is 5.83, which corresponds to what we were meant to get at the end.
These graphs show the conversion and selectivities of the sugars, and this shows the selectivity increasing for 2 of the sugars within the fermentation step and decreasing for glucose. This decreases due to the increased conversion of the glucose as the yeast prefers it. Glucose inhibits maltose, and both glucose and maltose inhibit maltose.
Currently the code runs controlling the jacket temperature instead of coolant flow rate. Changing this will be one of the modifications to be made. Currently our code runs so the cooling jacket is on as soon as the simulation begins to control the temperature. Usually at the start of the fermentation process you would let the mixture temperature naturally increase to its recipe temperature, in this case 20 degrees C. This is another modification that will be made. These are the dynamic tests that will be individually completed by the group in this semester 2.
I'm Isla from Group 11 and I'm just going to talk you through my dynamic testing, which is cooling failure. So how I'm going to simulate cooling failure is that I'm going to simulate restricted flow in the jacket by changing the limits of the controller. I'm also going to simulate no flow for the jacket as if there's going to be stagnant cooled fluid and see what effect this would have on the exotherm of the reaction. I'm also going to look at changing the area of the jacket to see what effect this has on the heat transfer through the jacket itself.
Changing the aspect ratio will change the dimensions of the vessel but will keep the volume at its original value. This may change the temperature regime within the vessel as the heat transfer area will remain the same. The temperature may go above a critical value where the yeast productivity could be affected. It is therefore important to understand what other parameters can be altered to keep the temperature at the required values. This dynamic testing will alter the aspect ratio and in turn understand what other parameters can be changed to keep the temperature at its required values.
I plan on adding disturbances to the process, such as disturbances in coolant flow and coolant temperature. I will analyse how this impacts control performance and also the flavour and ABV of the beer. To do this, I will add the disturbances as random events in the piecewise integration. One further dynamic testing that I could be able to evaluate once the code is modified is delays in the control switch once the exotherm reaches a certain temperature, and again analyse how this impacts control and the beer.
I'm Rachel, and for my dynamic testing, I'm going to attempt to make different beers, such as an 8% double IPA, by altering parameters such as initial fermentation time, or the time of the different steps, and the temperature at which these steps occur.
The most commonly used coolant in the brewing industry is a propylene glycol and water mixture. It is very important to use the proper percentage of glycol to water in the system. Not enough glycol could lead to the system freezing up and possibly cause the chiller evaporator to rupture internally. Too much glycol will drastically reduce the chiller system's efficiency. My dynamic testing will involve varying the ratio of water to glycol in the coolant solution to see how the reaction rate is affected. The code will need to be modified so that it calculates the coolant mixture density and specific heat capacity depending on what ratio of water to glycol is inputted.